Thank you. Thank you very much for the organizers for having us all together to learn about friezes. So I want to tell you about the connection to representation theory, but since this is the first talk, I think it is my great pleasure to give you the introduction of friezes and the Conway Coxeter theorem to get us started. This is where the story of friezes began. So just very briefly, let me remind ourselves what are Conway Coxeter friezes. So a Conway Coxeter frieze is an array of numbers such that, all right, so I'm going to start with the row of zeros. Then I'm going to have a row of ones below. Then I'm going to have some numbers, which I'm going to denote by stars, and they follow this pattern. Okay, some more stars at the end. So I have a finite number of these. I'm going to finish off with the row of ones, and finally the rows of zeros. Okay, so that's what a frieze pattern looks like. And what are my conditions on this array is, so the first one is that entries are positive numbers. So later on, we'll assume that maybe entries are just integers, or there's more generally some entries in some field or ring, but for now, let's say they're integers. Then we have the famous diamond rule. All right, so what does the diamond rule tell us is whenever we have a diamond, the neighboring entries, A, B, C, D, like this, then I want to think of it as a matrix, so I turn it sideways, and I read off, this becomes my first row, this becomes my second row, and the determinant, which is BC minus AD, is 1. And the last is called tameness, or let's just say tame. So we always are going to assume our friezes are tame, or our frieze patterns are tame, is that the determinant, so let me just say that a 3x3 diamond has determinant equal to 0. Okay, so if you consider a 3x3 diamond, you turn it to the side, you make it to a matrix, you take its determinant, then that is 0. Okay, so these were introduced and studied by Conway and Coxeter in the 70s. And then we have this very nice result. Okay. Okay, bye-bye. All right. All right. And then, okay. Right, okay, so the first thing before I want to state the result is we have the following, is first non-trivial row of the frieze is called quiddity sequence. Okay, so that's the first row of stars we have up there. That's the first non-trivial row. And so if you think about it, it uniquely determines the rest of the frieze because you have the diamond rule. The diamond rule tells you how to determine the rest of the entries from the initial one. So this determines the rest of the frieze. Okay, perfect. And so here's the theorem that 73 is we have a bijection between, let's see, friezes. So sometimes I'm gonna say Conway Coxeter friezes, sometimes I'm just gonna omit. So friezes of, okay, width n. Okay, since it's so far up, so width is the number of non-trivial rows. That's the number of rows which have stars in them. So number of rows in the frieze without the zeros and ones. There's a bijection between these and triangulations of n gons, or n plus 3 gons. Right, so we have this correspondence. So this very beautiful theorem, it led to us all being very much fascinated by friezes. So maybe, can you see well here, or the computer is blocking? Okay. All right, so let's do an example, very brief example. Okay, so let me start with a polygon. So this is going to be a running example for today's talk. Start with a hexagon. I'm going to write the triangulation here. So this is n equals 3 case. And then I'm going to go around the boundary of my polygon, and at every vertex, I'm going to record the number of triangles in the triangulation. So here's, I see 1 triangle, this vertex sees 2 triangles, this vertex sees 1, and this one sees 4. Okay, and the frieze I'm going to get out of this is I start with my row of zeros, my row of ones, and then I need more. Which one do I want to start with? 1, 4. So I'm going to start with this, and I'm going to go 1, 4, 1. Okay, I'm going to go clockwise around the boundary. So 1, 4, 1, 2, 2, 2. Okay, and so this gives me the first non-trivial rows going around the boundary of my polygon, recording the numbers I wrote down, gives me the first non-trivial row of the frieze, and then I can compute the rest using this diamond rule, which tells me 1 times 4 minus 1 times whatever's here is 1. So then you know that this is 3. Okay, 3, 1, 3, 3. And then you keep going, and 2, 2, 2, 1, 4, 1. Hopefully. Okay, and then I finish with the rows of ones and the rows of zeros. All right. So this is the story we have from the 70s of Conway and Coxeter. And so our goal for today, or for these lectures, is to describe the connection to representation theory. Between these frieze patterns, these friezes, and quiver representations of representation theory. Okay, so I want to reinterpret this picture in terms of representation theory. Not just the first row, but also all the entries, and give them a meaning in terms of representation theory. Okay. Oops. Hopefully that's okay. Okay, so I'm going to start now with the basic quiver representations. Introduction to quiver representations. Okay, so Q is going to denote my quiver, and it consists of the set of vertices and the set of arrows. So this is a quiver. Or in other words, a directed graph. Q0 are the vertices, and Q1 are the arrows. Okay, so our maybe small running example for this is 1 goes to 2 goes to 3. That's a quiver. 1, 2, 3 are my vertices. My arrows are alpha and beta. Okay, out of here, I want to create a path algebra. And so let's just say path algebra over the complex numbers. So this is path algebra. So what do I mean by this is a C vector space. So it's a vector space over C with bases given by paths. In my quiver. And so, for example, in here I have a path alpha, so that's one basis element. I have a path beta. I also have a path alpha beta, and so on. And then, okay, so that's as a vector space, and then this is an algebra, so I also have multiplication. And multiplication is given by concatenation or composition of paths. And multiplication is composition of paths. Okay, so if I can multiply the paths together and get a new path, then go ahead and do it. Otherwise, if multiplication does not make sense, so for example, if I do beta and then alpha, this is no good. This is not a path in my quiver, so I just let it be 0. Okay, so we're not concerned maybe with this as much. We're mostly interested in the category of modules over this algebra. So, okay, this is somewhat strange. Let's go here. Okay, so more interested in the mod CQ. So that's the category of modules, finite dimensional modules. Over the algebra. And as it turns out, so if I write this, this is quite abstract, but these objects can be made quite concrete. This is the same as the category of quiver representations. And so this is often denoted rep Q. Well, I guess I don't need parentheses. So just the rep Q. And so I'm gonna use these terms simultaneously or interchangeably, modules versus representations. Would be the same thing. And so these objects can be quite concrete. So let me explain you what are the objects and the morphisms in the category of rep Q. Okay, so what is this rep Q? Okay, so the objects are quiver representations. Okay, I really write big. Okay, so I can still do objects. So what are my objects here? So quiver representation is object M, which is a collection of mi and phi alpha, where I is a vertex and alpha is an arrow. So what is this mi? Mi is a finite dimensional C vector space. And this is a linear map. Okay, so maybe I can now make it go up. Oh no, these are manual. Perfect. Okay, so in our example, so what do? I put some finite number of copies at C of each vector space at each vertex and some linear map in each of the arrows. So, for example, M could be C squared, C. So that's and then I have to tell you what the maps are. And so let's say it is 1, 0, and 1, 0. Okay, so this is an example of a quiver representation. So I tell you what the objects are. I also can tell you what the morphisms are. So what are the maps? So given two quiver representations, I can write, okay, so what is a morphism? So morphism is a collection of linear maps, Fi for every vertex of the quiver, such that Okay, let's say this morphism goes from M to M prime. Okay, so here's the nice diagram. I'm going from M to M prime, and this is my map F. So at each arrow, so suppose I have an arrow, so alpha is an arrow I to j. Then in my quiver representation M, I have mi at position I, mj in position j, and a linear map between them. I have the same for the M prime. And then the F tells me at each vertex I have a map for the vector spaces. And then to be a map of quiver representations, this has to commute for every arrow alpha. So I guess this is phi alpha prime. Okay, so in our example, if this is M, I can write another representation M prime, which let's say is C0, and this map here is identity. Then I can write a F. So there are many maps between these two representations, but for example, so on this, let's say I'm going to have identity. On this, I'm going to have 1, 0. And on this, I have no choice but to be 0. And you can check that each of these squares commutes. Commutativity happens. And so this is indeed a map of quiver representations. Okay? Questions here? Okay. Just a little bit more. So, okay, so just as with modules, we can take direct sum of modules. So same with quiver representations. We can do the same. So what is a direct sum? So I can do, let's raise it up so you can see better. I can take a direct sum of two representations, M plus M prime. And so all it is, for each vector space, I take the direct sum of the corresponding vector spaces. And then for linear maps, you just do the diagonal. Okay. So that's what the direct sum looks like. And then, as with anything, if you want to understand the category of modules or the category of quiver representations, you really want to understand the indecomposable ones, or those which do not come as a direct sum of two objects. And then, well, you want to recognize when is a quiver representation a direct sum of two. That's not always easy, but for the nice ones that we have here, it is not too bad. And so in our example, we started with this M, which is C to C squared to C. And the maps are 1, 0, and 1, 0. Okay? So now you just think about what is happening here. So here you have a single vector space C. It goes via 1, 0 into this two-dimensional space. So it goes into one of the two copies in here. And then the same copy of C is being mapped into here via identity. Okay? So really, this copy of 1 goes into here, and that's via the identity. And then there's a second copy of C sitting here, and nothing comes into it, and nothing comes out of it. So it's kind of separate. So it is not too hard to convince yourself that this is a direct sum of these two. 0, C, 0. Okay? And so this type of logic, for this particular quiver, you can use to find all the indecomposable representations. All right. Let's see. Okay. Okay, here comes the challenging part. Trying to erase. Yes?
Should it be clear yet to me why I should be thinking of these as representations?
Why are the modules the representations? How are these modules?
Or in what sense are they?
Yeah, so you can define the act. So given this M, you can act on it by an element of the path algebra, like a path, like let's say an arrow alpha. And so what do? You have this vector space. So let's say I'm here, c squared c, and I want to act on it with a, okay, so I choose an element. So I have some element in here, some element in here, some element here. I act on it by the path alpha, let's say the arrow alpha. You see what alpha does? It moves things from 1 to 2. So all it does, it's going to pick up an element here, apply phi alpha to it, and the output is the element there. And then it turns out, so that's a theorem, that every module over actually any associative, finite dimensional associative algebra can be represented as a path quiver over path algebra. And then the modules over one come from representations of the other. Yeah. Other questions? Okay, while you ponder, oops, don't go up. Okay, all right. I have not used these before, so bear with me. Ah, okay. Listen. Oh, you mean go this way? Oh, okay, technique. Uh-oh. More water? Yes, okay, thank you. Okay, the second speaker should take notes. Uh-huh, thank you. This, okay. Okay. And I use this as well? Okay. Okay, okay, okay. I apologize. Okay. Okay. Perfect. Okay, that was a nice pause. So now we can talk about the something called the Auslander writing quiver. So as I said, if you want to understand the module category, we need to understand all of the indecomposable representations or modules, those which do not split up as direct sums, and then all of this data can be recorded in the Auslander writing quiver. So actually not just the indecomposable object, but also the irreducible maps. So it's a quiver. So again, I have to tell you what the vertices and the arrows are. So the vertices are indecomposable representations of a given algebra, and then the arrows are the irreducible morphisms. Between them. Okay, so let us do the example in our running example. So let's say we have the path algebra of the quiver 1, 2, 3. then it turns out all the indecomposable representations, we can classify those. So for today's lecture, all the representations are very nice. So, okay, so it is not hard to see that this is indecomposable. It's one-dimensional. You cannot decompose it any further. It's a simple representation. You also have one at vertex 2. You also have another at vertex 3. Okay. And then you can convince yourselves that if I just put CC, copies of C at the neighboring vertices, put the identity between them, and these are also indecomposable. And the last one is I just put copies everywhere, and here I have identities. Okay, so it turns out these are all. So there are just 6 indecomposable representations for this quiver. And here's where we're going to use a different notation to sort of compactify this slightly. So instead of having C00, I'm going to write this, denote this representation as 1. This means I have a single copy of C in vertex 1, position 1. Here I have a single copy of C in position 2, so I'm going to write this as 2. I have a single copy of C at vertex 3. This is a 3. Now here I have copies at vertex 1 and 2, so I'm going to have 2 numbers here, 1 and 2. Because there's an arrow from 1 to 2, I'm going to stack them vertically, 1, 2. Here the same, this is 2, 3. And the last one is 1, 2, 3, and they stack one on top of the other. Okay, so that's my shorthand notation. And then the AR quiver, also on the right-hand quiver, it turns out is as follows. In this notation, let's see, perfect 3 goes to 2, 3, 1, 2, 3, 1, 2, 1. Okay, so that is the quiver. So I have all my indecomposables here, and the arrows correspond to my irreducible morphisms. And it does have this distinct shape, which will be important to get us back into the world of friezes. Okay, we're going to go back here. So hopefully you see a diamond here. This is a diamond, and this you will make sense of it as a diamond for the frieze. Okay, questions here? Sorry, could you repeat the first part? Mm-hmm. Yes. No. So in general, if you have a more complicated quiver, so actually if you don't have 3, but you have 1 and 2 arrows from 1 to 2, in that quiver you will have 2 arrows from between, let's say, 2 indecomposables. So yes. So these are very, very nice. These are what's called type A quiver representations, and so lots of nice things happen here. Yeah, that's a good question. So these can be much more involved, these AR quivers. Okay, so other questions? Very good question. Okay. Okay. And I'll explain how to construct this quiver, I guess, from the triangulation picture. Okay, so you will see maybe you'll be able to do more general ones if you're not familiar where this is coming from. So slightly more generally, we can construct, so here we just looked at the path algebra, but I can do something like this. So I can take a quotient of a path algebra. So this is quotient of path algebra by some ideal. And we usually call these ideal of relations. And so then it turns out that the modules over this algebra, again, are equivalent to representations of Qi. So I have to also give it some data of this ideal. And so the way to think about it, these are quiver representations. So these are representations of Q satisfying relations in I. And so I'll give you an example of that as well. Yes?
So the path algebra is kind of an algebra with a partially defined composition.
What do you mean? So I can multiply any two elements together.
Oh, because you say you define it as zero if you cannot.
Yes, yeah. So it's a associative, finite dimensional associative algebra.
Okay.
Yes.
And so the ideal here, you're taking a left ideal, a right ideal, a bilateral ideal.
This is two-sided ideal. Mm-hmm. Okay. Okay, don't drip. Okay, so I just want to give you a quick example of this. In case you have not seen that, to give you to explain what I mean by more representations satisfying the ID, the relations in I. Okay. Right. Oops. Okay, maybe let it dry. Let's go here. Oh, I have to erase again. Okay. Well, I think I still have to erase it. Maybe I'll erase that while that one dries. Okay. Mm-hmm.
So you said you start with the quiver, and then on the quiver you will also have the operating quiver, including all the reducible representations and the morphism. So now if you take any representation of your initial quiver, you can view it in this quiver as just saying I've got weights at each reducibles and weights for vertices, and you don't care about, I mean, if you just know the weights, you don't need to know the order of how.
Yeah, so these categories, they are Krull-Schmidt. So every object, every module is a direct sum of indecomposable ones, so sum of these, and the order doesn't matter. Yes, up to reordering. So there's a unique way to decompose. Every representation is a direct sum of indecomposables.
And so what would be the pedantic way of saying the relation between the initial quiver and the Austrian rating quiver?
So that's generally a very complicated thing to construct the AR quiver. In these type A ones, I will tell you how to do it.
But what I mean is that so the representation theory of the quiver you started with is so it's just the same thing as something which should be very simple, like which has probably just a name, like just weights on the edges and vertices of this automatic quiver.
So just the vertices, just the weights on the vertices, because you just need to know which summons make up the indecomposable. You don't need to know the arrows. If you know, the arrows tell you the morphism between the objects. So if you have two objects and a map between them, then you need to know the arrows as well, your weights on the arrows.
So you just need the weights on the arrows.
Vertices.
You just said before that sometimes there are
Yeah, but so here 3 is like an indecomposable representation. 2, 3 is an indecomposable representation. I can take a direct sum of these. So I get an object 3 plus 2, 3, and I don't care that there's an arrow between them, right? So being a representation or being a module doesn't care that there's map between them at this point. Sure, yeah, that's a way to think. Yeah. Okay, so what is if we have relations? So suppose I have, again, this quiver, 1, 2, 3, alpha, beta. And for example, I can take my ideal I to be something generated by the path alpha, beta. And so what is this rep qi? So rep qi consists, so what are the quiver representations? So again, I'm going to put vector spaces M1, M2, M3 at each of the vertices. I'm going to have some phi alpha and phi beta. So if I don't put any restrictions, any quiver representation of Q is this. But because I have the condition, yeah, in my path algebra, I'm going to take KQ mod I. So this alpha beta is going to be 0. What this means is I have to put the restriction that phi alpha composed with phi beta is 0. So for example, this quiver representation CCC, which is identity everywhere, CCC, and the maps 1, 1, that's not a quiver representation of CQ mod I. Okay. So the relations alpha beta and the maps have to respect the relations. Okay. So now I want to tell you how to sort of get this AR quiver and get us closer to from the triangulation. So we're going back to this Frieze pattern. So from triangulations to, let's say, Jacobian algebras. Okay, so what I mean by a Jacobian algebra is just a particular algebra, which is going to be a path algebra of a particular quiver coming from a triangulation T, modulo some ideal. So T is a triangulation. Okay, so maybe I should say that again. So T is a triangulation of a polygon. And so here, okay. Okay. So from the triangulation, I'm going to tell you how to explain how to get the quiver. And once you know the quiver, you can get the Jacobian algebra. Okay, so here in the triangulation, I have arcs. And the arcs in my triangulation, or the diagonals in my triangulation, are going to correspond to vertices of the quiver. And then I want to tell you how the arrows look like. So the arrows are, let's say, I to j. And so in this triangulation picture, I'm going to have an diagonal I, a diagonal j. And I'm just going to fix a convention that my arrows come counterclockwise. So whenever I see this in the triangulation and there's nothing else in between, so this is part of the triangle, I'm going to have an arrow from I to j in the quiver. Okay, so in our example, yeah, why not? Let's do it here. Okay, so what do I mean? So for example, this is a triangulation of a hexagon. I'm going to label my arcs in the triangulation or my diagonal by numbers. So let's say 1, 2, 3. Okay, and then I want to, so that means my quiver is going to have 3 vertices, 1, 2, and 3. And I'm going to go, I'm going to look at my convention. So I see that I can go from 1 to 2 in a triangle in a counterclockwise direction. That's going to tell me I'm going to have an arrow from 1 to 2. I can go from 2 to 3 in a counterclockwise direction. So you have a 2 to 3. So my quiver is the one we've been working with. So 1, 2, 3. Okay. We can also do slightly more. I'll show you another example. Oh, okay. One more thing I want to put there. Okay, so that's how to get the quiver. And then if you don't have any cycles in this quiver, so there are no cycles, so the Jacobian algebra in this example is just the path algebra of the quiver. Okay, there's no relation. On the other hand, you may have relations as follows. So if I look at still a hexagon, but I have now a different triangulation. 1, 2, 3. Okay, so I still have 3 vertices, and I have now an arrow from 1 to 2, 2 to 3, 3 to 1. So 1 to 2, 2 to 3, 3 to 1. Okay, so that's my quiver. So now you do have cycles, and then, well, you have to do a little bit more. So the Jacobian algebra, J sub t, is the path algebra of the quiver. So if I just did this algebra becomes infinite dimensional because you can take there are infinitely many paths in this quiver since you can go as many times as you want in a cycle. And so it turns out to make everything work, you have to quotient out by an ideal. And this ideal is always composition of paths in 3 cycles. So you will only have 3 cycles in the quivers coming from triangulations of polygons. And so I would always be defined by, you have to kill these cycles, and so, or set them equal to 0, and so you mod out by the ideal. So in this example, if I call this alpha 1, alpha 2, alpha 3, then the ideal I is generated by alpha 1, alpha 2, alpha 2, alpha 3, alpha 3, alpha 1. Okay. Yes?
Why are you not putting the triple first?
So it's already will be in here as well. So if I take, so this is the generating set for the ideal. I can multiply it by any element of the algebra, and it would still be in the ideal.
Why do you want to take all of those?
This turns out to be the right thing for the combinatorics to match. Yeah.
So maybe my question is, what does it mean to be, what's the definition of composition of paths in a 3 cycle?
What is it? So if I do alpha 1, alpha 2, alpha 3, this is an element in the path algebra. And and in the quotient, it becomes 0.
Oh, so this is the quotient.
Yes, this is the, so this is the ideal, and then my algebra is the path algebra of the quiver modulo this ideal. So all of anything which has either alpha 1, any of these. So if you think of all the paths in here, if it's going to have a subpath which is any of these, it will be 0.
I mean, a way of saying it, you have 2 opposable arrows in the same triangle.
Sure. Yes.
And then it's clear that everything is generated between.
Yes. So composition of any 2 arrows in the 3 cycle becomes 0 in the quotient. That's what that means.
Maybe you want to write composition of arrows.
But so alpha 1, alpha 2 should be 0. That's what you say, man.
Yeah, so like alpha 1, alpha 2 is 0 inside this. All right, very good. Okay, maybe I erase this and then erase more. Yes? Yeah, so they will share side in the triangulation. In the quiver, they will just share vertex. So, okay, so in the triangulation, you can have something like this. 1, 2, 3, 4, 5. And so in the quiver, you're going to have 1 goes to, 3. 3 goes to 2. 2 goes to 1. That's for this. And for this one, it would be 3 goes to 5. 5 goes to 4. 4 goes to 3. Okay, and so the rule, again, composition of any two arrows in this cycle is 0 and in this cycle is 0. But I can go from this to this. I have 4, 3, 2 is an allowed path. You will never have things, so coming from these, from polygons, you will never have things like that, yes. The enumeration of the paths. The number of paths will be the same. Indeed. For every polygon, whatever triangulation you have, the associated Jacobian algebra will have the same number of. Well, it's how the same number of indecomposable representations, and that's, yeah, it's the same number as paths. It's the same dimension. Yes. Okay, so here's we go back to representations. So this is the work of Caldero Chapoton from 2006. Again, T is a triangulation of polygon, as what you have is, if you look at diagonals, in polygon, which are not part of the triangulation, then these correspond to indecomposable JQ modules, or JT. Okay, and the correspondence is very nice. Okay, so maybe I want to draw a very nice picture for you. Okay, so just to illustrate how this works, I'm going to have a running example again. I'm going to have 1, 2, 3. And now I'm going to choose a diagonal here, which is not part of my initial triangulation. So let's try to choose this diagonal, gamma. And so what representation I'm going to associate to gamma? Well, it's going to be, you kind of read the crossings of the arc gamma with the diagonals in the triangulation. So it crosses 1 and 2. So I'm going to have a copy of C in position 1. I'm going to have a copy of C in position 2. And okay, they are next to each other because they're in the same triangle. So that will be identity map 0. Or in our notation, this is the quiver representation 1, 2. Okay, so because it crosses the arcs 1 and 2, really you will have numbers, your dimensions will be 1 and 2, and you just put them together. And so any arc that I'm going to draw here, which is not part of T, is going to give me an indecomposable representation. So let me do a nice picture now. Okay, so I'm going to redraw my quiver again. Yes? So if I have any quiver representation which satisfies these relations, I will decompose it into quiver representation, which will still satisfy this relation. Yes? Mm-hmm. Okay, and so, okay, I need another color. Green. Let's say I'm going to label my vertices 1, 2, counterclockwise as follows. Okay, so we said that the arc gamma corresponds to representation 1, 2. I'm going to now denote gamma by the endpoints. Okay, so gamma corresponds to an arc with endpoints 2, 5. Okay, so where 1, 2 is, I'm going to write 2, 5. Okay, it corresponds to the arc 2, 5. For example, if I want to know the representation, which arc corresponds to the representation 2, it's the arc which is just going to cross the arc 2, so the white 2. This is going to have endpoints 2 and 4. So here I'm going to put endpoints 2, 4, and so on. Okay, so every arc which is not already in my triangulation corresponds to a quiver representation, and the endpoints are there. Did I move? Module 2, 3, thank you, is 1, 4. Yes. Yes, good. Okay, and now, so this is the AR quiver, this is this. How do we finally get back to the Frieze picture? So we need to do a bit more. So you see in this picture, if I go to the right, all I do is I add 1 to the endpoint. So this is 1, 3. If you just think of the green here. So 1, 3, 2, 4, 3, 5. So I just keep adding 1 to the endpoints. Mod 6, since we are in a hexagon. So let's just follow the rule and see what happens. So here, if I added 1, mod 6 to this one, I would get vertex with endpoints 2, 6. If I did it here, 4, 6. I subtract 1. And I want to do one more, okay? I did it here. 3, 6. Okay. Okay, one more, last one. 1, 3. And 4, 6. Okay, so 1, 3 is the same as here. 4, 6 is the same as there. So 1, 3 corresponds to representation 3. 4, 6 corresponds to not a representation. Okay, so now we go back. So 4, 6 is this arc. So it doesn't cross anything in my triangulation. So I'm just going to denote it as T1. Okay, it is not a module. It just corresponds to an arc with label 1. Okay, same with 2, 6. 2, 6 is T3. 4, 6 is T1. And 3, 6 is T2. Okay, so by completing the AR quiver, by adding arcs, which are in my triangulation, I get now this very regular type of pattern, which now should mimic the Frieze pattern. Okay, that's the idea. And so here's the theorem. Perfect. Right. Well, okay, no, I do want to keep this one. So, all right, here we go. Okay. All right, so here's the theorem, okay, which is attributed to Caldero Chapoton. Again, from 06. So if you look at the AR quiver of the algebra, the Jacobian algebra, yields, so this AR quiver yields Conway Coxeter frieze after specializing as follows. So if I do, okay, this is the specialized Caldero Chapoton map, so it's a map and it's, okay, so I put a tilde on it. If I evaluate it at these TIs, these are summands of my, or elements of my triangulation, I'm gonna get a 1. And if I evaluate it on an actual module, what I get is the number of submodules of M, well, up to isomorphisms.
Number of submodules. I don't think it makes a difference in type A.
Okay. But it's still up to isomorphisms, right?
Well, I mean, it doesn't make any difference. I think it's misleading. Anyway.
But I mean, if I have if I have like instead of 1, I have an A, these two quiver representations are isomorphic.
As representation.
Yes.
Yeah, but if we're going to generalize later to Kronecker or something,
Oh, no.
you shouldn't say this because it's.
Oh, yeah, no. I'm not going to Kronecker.
Then you don't need it for answers.
Okay. Is this better?
Yes.
Okay. Okay, so if I do this, AR quiver, oh, okay, that's it. That's the statement. Okay. So so in other words, I have this picture. All I do now to get my frieze, which is over there, finally, what do? Let's have another color. Is so the summands of T, they just become 1s. So that's a 1, that's a 1, that's a 1, and that's a 1. Okay? And now, for all the others, I count submodules. Okay, so 3, the representation 3, this is one-dimensional at vertex 3. So if you think of submodules, you have the 0 submodule and itself. It is nothing, it is a simple representation. So this has 2 submodules. Similarly, this, same, 2 submodules, 2 submodules. Okay? Yes, good. 2, 3, now let's look at the quiver. So 2, 3, I have the 0 representation. I have itself as a submodule, so you always have 2. And then you see this 3 actually embeds into 2, 3. So this is a different representation, which is a submodule here. So it has 3 submodules. Okay? 1, 2 similarly has the 0 representation itself and the 2. 2 embeds into the 1, 2. And this one would have 1, 2, 3, 4. 3 has a 1, 2. Okay, so that's it. So so maybe. Yes. Yes. Okay, so good. So once now, if you read the numbers 1, 4, 1, 2, if you go up there, the first non-trivial row is 1, 4, 1, 2, 2. So if I kept going, I would, and this is 3, 3, 1. That's kind of part of the second row, 3, 3, 1. And the 2, 2, 2, 2, 2, 2, that's the third row. So this gives you the non-trivial rows in the Conway Coxeter frieze. So counting submodules of these quiver representations corresponds to all these non-trivial entries in the frieze. Okay? Perfect. Okay, I'm almost out of time. So let me say, what do I want to say? Right, so that's the connection to representation theory. So one last thing maybe, because I promised M&A I would say this. More generally, So there I put a tilde. There is something called the Caldero Chapoton map. Okay, which takes in a module and it outputs a Laurent polynomial in the variables xi. So I'm just gonna write it. I won't explain too much about it, just in words. Where is it? There it is. Okay. X to the index of m, sum. Okay, so this is something called an index, and it comes from the injective presentation of m. Okay, so it's some vector. Okay, x raised to a vector. So this is some monomial in x. E is a dimension vector. So it's sum over dimension vectors. Euler characteristic of the quiver Grassmannian of M, x to some matrix, BQ of E. Okay, so this is Grassmannian of submodules of M of dimension vector E. Okay, this is some Euler characteristic. And this is a matrix. This is the, what do you call it, adjacency matrix of a quiver. Okay, so the point I want to make is, given a quiver representation M, you can define some sort of, more generally a polynomial, a Laurent polynomial in X's. So this thing, which comes from like properties of the module. So this is a Laurent polynomial in x1 plus or minus 1, xn plus or minus 1, where n is the number of vertices in your quiver. And in particular, yeah, so this actually counts submodules. In type A, this Euler characteristic is either 0 or 1. It is 0 if there is no submodule of this dimension vector of M. It is 1 otherwise. So in type A, if I specialize all the x's to 1, I recover that formula, CC tilde of M. So CC tilde of M is the CC of M specialized when all the xi's are 1. Okay, so in type A, it counts the number of submodules. More generally, you get some Laurent polynomial. And the point is, if I now, in my AR quiver, if instead of having these numbers, I just put in these values CCM, I get some Laurent polynomials. And so what I get is some Frieze-looking pattern where the entries are now Laurent polynomials. And it turns out the diamond rule, this diamond rule that we have for Conway Coxeter friezes, as well as tameness, they're all satisfied for these Laurent polynomials. So you get a frieze with entries xi instead, and then specializing the xi's to 1, so you recover the Conway Coxeter frieze, right? Okay, and I will stop here. Thank you.
Thank you very much. Okay, thank you very much for this very interesting introduction to representations on friezes. Any questions?
Hi, maybe skipping ahead, maybe you'll talk about this later. Or, is there a way of interpreting friezes in type AN? The numbers as dimensions of modules of some category? So this is not quite, right? This is sort of a clever, slightly cheeky way of doing things, but it's not quite sort of, just count dimensions of certain modules.
So in general, you have to count these.
But this is this is somewhat awkward because Euler characteristic not in general positive, right?
Yes, but for quiver representations, or maybe just I think quiver representations, it will be positive.
I think not in general. I think quiver.
For what? For in general, no. Okay, for Jacobian algebras, let's say. And if you associate, like for things coming from cluster algebras, then yes, I didn't talk about cluster algebras. So if you're doing like generalizations of friezes and things like that, for other not just type A things, then this would always give you positive things. Yes, but in general, you're not counting submodules. That's right. You're counting submodules up to something with maybe some multiplicities. You kind of have to look how the submodule embeds into the module, and that's where this comes in.
Thanks.
Yeah, it becomes more involved.
I almost feel like it's like this is, you can use this, you know the frieze is positive, so this becomes a statement. All the other characteristics here are positive. It feels more like that way rather than it's not manifestly positive.
Yes, this thing is not manifestly positive. But for nice modules, the ones we will generally care about, these will be positive. Yes, even for more complicated modules. But yes, but in type A, it's all nice.
I mean, it's not an accident that positivity postdates this formula by 15 years. Like it was an open conjecture for many, many years that this formula existed.
This is what I mean. Somehow this is.
Yeah.
Okay. Oh, one more question.
Yeah, so in the one example, sadly it's now been erased, the one where you had the ideal was for the 3 cycles, and you had it generated by all those pairs of 2. It makes sense that, yeah, if you add something else, then you do get a 3 cycle and it's 0, or if you put anything else, you then have a double. Like you'd have alpha 1, which gives you 0.
But you cannot do alpha 1, alpha 1?
Yeah, because it would
sure.
be 0.
Yes.
So I guess, is it obvious why having those 3 pairs generates the ideal that would give all 3 cycles?
So I think this was the discovery of Caldero Chapoton Schiffler, that this is the right ideal, which gives you exactly the Jacobian algebra, which gives you the correspondence to the diagonals in a polygon being indecomposable modules.
Okay. Okay. So there's.
So it's like for it to make it work, that's what happens. In general, you have something called the Jacobian algebra and the potential, and then it comes out as like more general theory. But for type A, it was I think it was discovered this way.
Okay.
Okay, then let's thank Khrystyna again.
Thank you.